Hello and welcome to Azure Cosmos DB Conf 2022. My name is Santosh and I will be talking about how event sourcing and serverless have powered e-commerce systems. Today's agenda is pretty simple. We'll talk about why e-commerce is complicated, talk about some modern principles like event sourcing, caching, serverless, change data capture, and others that help alleviate these issues. And we'll kind of do a short demo encapsulating all these concepts. So let's start with e-commerce. So this is a typical online shopping cart. This has been around for over 2 decades, pretty much looks the same on most e-commerce websites. The customers browse the website. For electronics, they filter by laptops and then land on this page. It may or may not show some recommendations. The item availability is served via an API. When the customer checks the e-commerce website, it cannot be done and it can't take too long to load. That's because the customer's website is just a tab away. So as a result, e-commerce websites often have to have serious SLAs. So think of 4 nines SLAs, 1 hour downtime, and they also have to have faster response speed. So think about 300 milliseconds loading time or less. I'll dig into a small piece of functionality of this website and talk about how this is served by some of the concepts that we discussed. So let's say the customer wants to buy a laptop. The general process here is the customer adds the laptop to the cart. When the customer is ready to check out, they set the delivery address and pay for the laptop. Now, most e-commerce systems really don't reserve a laptop for you until you go to the checkout page. So let's freeze at this point in time and say we are about to check out. Is the laptop still available? Or is it available at a nearby store? Or is it going to be at a warehouse? Did someone else snatch up the laptop at the last moment? Let's think about serious traffic times like Black Fridays or Cyber Monday or something. How do these systems work in those cases? So we'll take a simple e-commerce reference architecture. Most people are probably familiar with eShop on containers, which is on the Microsoft architecture website. It's a pretty awesome architecture for small to medium businesses. So you have identity microservice, you have catalog microservice, ordering microservice, and so on. But when it comes to larger e-commerce systems, each of these individual components can get way more complicated. So let's drill into the catalog and ordering microservice for this particular example. So in a lot of legacy systems, you often see that the catalog services often use relational databases. So in order to load the catalog, it has to check with all this data. So check the products, categories, brands, models, and these are just a few tables are named. In reality, it's much more complicated. So if you're using a relational database, just these 4 tables or just these 4 sets of data, what do they look like? They often resemble something like this. So the data is stored in a disassembled form, aka shredded. For each product item in the list, the data is read by reassembling these objects. This is called the object relational impedance mismatch. In this example, at the very least, you would have to invoke data from a minimum of 13 different tables every time you want to view the product details. Now, multiply this by a billion records. What does that look like in a real e-commerce website? So you have, in addition, you have a request that travels from the website to the database, to the 13 different tables, and then back. So that's some serious latency. Now let's talk about the ordering microservice. The ordering microservice is often you see in legacy systems, they invoke other services. So in this example of the ordering microservice is actually an entire org. You hear about supply chain these days all the time. When the e-commerce invokes the ordering API, it has to check with all these other services. So you have warehouse, you have existing reservations, you have store inventory, which probably includes the floor and the back room of the stores. You have third-party inventory, which is like partners and suppliers. You have sales cap, for instance, seasonal limits for products like Xboxes. You have legacy systems, which may also contain duplicates that may have to be verified. And you have back orders that were not fulfilled. So what does a system like this look like? It looks something like this. Each service is represented by a box, and each of these boxes may be maintained by one or more teams. Each has its own service and likely multiple services and databases. What happens when customer wants to place an order for a laptop? They call the ordering API, which actually branches out and does a whole bunch of calls. So for instance, it may make a call to the warehouse inventory, not find any matches, go to the store inventory, and also have to check against reservations and back orders just to make sure that the item is available. And it has to go back and do the third parties and legacy systems anyway. And then when all of this is said and done, it has to check the sales caps. So you can see that we are making multiple API calls, often synchronously, just to compute one answer. So what happens in this scenario is that each of these services becomes a single point of failure. Let's say the system has 99.9% uptime and 300 millisecond latency, which means that every subsystem must have better uptime and better latency. So think about 5 nines of uptime and latencies less than 50 milliseconds. That makes maintenance really expensive. Additionally, for each call, each of these services needs to work correctly. Even if one service goes down, you risk giving the wrong answer to the customer, which is often worse than giving no answer at all. Okay, one service can take down the entire system. These are hard to test. Testing the dependency tree is not an easy task. You can do unit tests on small sections of the system, but doing integration tests for this type of dependency tree is a nightmare. Speaking of the state, the current state is stored in a distributed manner. It's stored in each system individually. So each system may have a relational database that stores the current state, and these have to be mutated in place. And we are assuming that to get all of these, there'll be no outages and everything stays up all the time. So let's take an example. You're making a call, I check the warehouse, is checking the store, and while checking the store, the reservation API went down. How does the system respond to such a scenario? So what happens? This code is basically distributed, unreliable, and expensive. To put it bluntly, servers are not reliable, and we have to account for downtime. So we use some modern principles like event sourcing, caching, serverless, chain data capture, and so on. So in this case, what we're doing is instead of synchronous API calls, we're switching to asynchronous message and log-based communication. The vision here is that the systems communicate with each other using messages. We use log-based pub subsystems like Event Hub, where the messages are ordered and retained for later consumption. And during an outage, we use checkpoints, so you can reset the checkpoint to a previous point in time before the outage. And this really enables fast, improves your mean time to recovery. You can usually leverage a service like Event Hub or Kafka over here. For events are facts about something that already happened in the world. And just because the current state of the system is different, that doesn't mean that the past event did not happen. So in event sourcing systems, events are first-class citizens. The data source is a ordered set of events, and the current state is just an aggregate of the ordered set of events. So take a bank account, for example. A bank account, your current balance is just the result of every deposit and withdrawal you ever made. An event sourcing system is like a time machine where you can see the state for any point in time and walk step by step for every state. What problem does this solve? It is easy to replicate the state of the system at any point in time. This is really great for debugging and analytics. You can leverage Cosmos DB in multiple spots in an event hub architecture. This brings us to stateless computations, and functions, serverless functions really enable this in Azure in particular. All business logic is stateless functions with zero external dependencies. You collect all the state you need upfront, often in the form of messages, and pass it into the code in the functions as parameters. The function is predictable, atomic in nature. There are no random outcomes, no partial results. Real-world failures will keep the code from executing, but it will not leave the system in an uncertain state. The domain logic is easy to test, and integration tests are often just connections between two different services, which are fairly easy to test. So functions are great because they are atomic in nature. They're scalable, and the integration code is abstracted away. So you're getting some state values. You pump them into the function. The function runs the calculations and provides results. And this is idempotent. It happens every time. So once the business logic is complete, then you have to write the data. So we follow a principle called write once. You write the data to the source of truth. But you cannot write the data to the database and then notify downstream consumers in the same process about these changes. Because what happens if the process fails? Your system gets into an inconsistent state. Dual writes exposes to this scenario. We use a method called change data capture to prevent this from happening. The change data capture is in the change data capture, the notification happens only after the commit is complete. So you never lose an event. Cosmos DB in particular provides a feature called change feed that enables change data capture. And then finally we talk about caching data. When you know the possible set of inputs in advance, you can often, for instance, in a product catalog, models, all of these, they don't change too often. So it's pretty safe to calculate them ahead of time and store it. So instead of real world computations, you do a pre-computed cache of results. This also works in data in systems where the events often are fast flowing. So you have a master database and you can cache your data into views in the serving layer. So Cosmos DB enables all of these, and you can use Cosmos DB both for the master database and the serving layer as cache. So putting together all these concepts, like caching data, streaming events, asynchronously, putting together all of these, what we can do is, instead of reaching out to each component during a call, we store the data every time a change happens. Let's say a reservation changes, you can push it down to a data store that's close to the API. So all the components are asynchronous, the messages are flowing from left to right. You're trading real-time computation for cache. So the hot part to calculate any availability would be basically 2 API calls instead of a dozen. And this you can often achieve with a system as low as 3 nines SLAs with 150 millisecond latency, which really decreases your cost of operation. So with that, we'll kind of do a demo that encapsulates all these concepts. And the one I picked for that is a demo that involves the event sourcing architecture on the Microsoft page. So the reason I like this is because we can plug in various Azure components as part of this, and it also shows how flexible this architecture is. Not only that, it also displays the various capabilities of Cosmos DB. So for instance, for the incoming events, we can use Event Hub, and then we use a router using Azure Stream Analytics. Cosmos DB is the source of truth. And also you can enable change data capture using the Cosmos DB change feed, which is captured by a function and gets stored as a materialized view. Excuse me. So with that, I will jump into my code. So I want to show the data that gets generated for this. So I am using a library called Bogus. This is a simple console application, and I'm generating inventory data, which includes location, count, inventory type, manufacturer, and action type. Action type includes ship or sale. If it's ship, then I'll reduce it from the inventory, and if it's stock, I'll add it to the inventory. So with that, let's go ahead and run this one. So when I run this one, it will generate a bunch of events, and where these events go to is they are pointing to an event hub. So I'm sending this to an event hub. So basically I'm generating all these fake data, and I'm using the event hub client, and for each of the item in the data, I just send it to the event hub. So this event hub, as you can see, I have a resource group. The resource group has a event hub, it has a stream analytics function, and Cosmos DB. So this is my event hub. My event hub will receive the data, and it has something called a consumer group. So what I'm going to do is I have a stream analytics service, and I'm going to connect my stream analytics service to the event hub. So my stream analytics service is connecting to the event hub, and then I can query the incoming results from the event hub, and I send it to the output of my stream analytics service. The output of my stream analytics service connects to a Cosmos DB instance. And in this case, it's a collection called inventory collection. So as you can see, my inventory collection has data that has been provided from this from my sample console application. Now, as data comes into this Cosmos DB collection, I have a Azure function that's running in the background, and this Azure function, let me reduce this. This Azure function, what it's doing is it's reading the incoming data, and based on the type of action, whether it's stock or ship, I add or subtract it to my catalog. So then I insert the data, and that data goes into my catalog collection. So that is a very simple example of how a very simple but powerful example of how Cosmos DB is in particular enabling event sourcing architecture and a lot of the modern concepts like the change data capture, caching, and so on. So with that, I will end this demo, and you can always get in touch with me on my LinkedIn or Twitter, and hopefully you get to implement some of these concepts in your e-commerce systems. Thank you very much.